See, when it comes to reaction mechanism, the basic terms what you need to know is that there is something called a substrate, a reagent, and a product. A substrate is something which is a functional group, which could be alkyl halides, alcohol, carboxylic acid, amines, something of that sort. Okay. And you would notice there are various types of reactions that usually happen in organic, around the organic compounds. First one is addition reactions, where either an electrophile is adding or a nucleophile is adding. Substitution reactions, either an electrophilic, nucleophilic, or radical substitution is observed. Then we have elimination reactions of various kinds, which is E1, E2, E1CB, EI. These are all the elimination kinds. Starting with simple addition reactions, if you notice, addition reaction is most often observed in cases of double bond and triple bonds. Now, the double bond could be between C double bond C or C double bond O. So first let us see between C double bond C how the addition reactions take place. If we have CH2 and CH2, which is ethene, on making a catalytic hydrogenation, which is adding of H2, you will get ethane. What are the reagents we can use? H2 by nickel. That means I take a nickel surface and I make hydrogen gas to get adsorbed on it and pressurize this ethene on top of it at a high temperature. Then most likely these hydrogens will start clubbing with this carbon, convert themselves into ethane, and then they will uh, escape away from the surface of the metal. Now, if you may have noticed, the hydrogens both are adding from the same side. If both the hydrogens are adding from the same side on a double bond, it is called syn addition. Syn always represent of a similar side. Am I clear so far, beta?
Yes, sir.
Right. Okay. One second. Right. See. Now, if we have a double bond and I make deuterium to add instead of H2, again in the presence of platinum, palladium, nickel, anything, you will get a syn addition here, which will lead to hydrogenation. Okay. If it is deuterium, you can call it deuteration. If it is hydrogen, you call it as hydrogenation. If you have a triple bond also, on adding D2, you would first get a double bond and then on further addition, you'll get a triple bond. These are the sources for making a nascent hydrogen. Nascent hydrogen means a hydrogen which is more of a radical form, H dot form. Okay. If you have a triple bond added to deuterium, right, then I would get this double bond. I can avoid the further addition of hydrogen or further addition of deuterium if I use the catalyst with a poisoned metal on surface, which means if I take barium sulfate or calcium sulfate, calcium carbonate, and start, brushing it over the surface of the metal on palladium specifically, okay, or I can take a nickel and brush with boron on surface of it, then what happens? The pores of that metal surface will decrease. Thereby, it becomes difficult for alkenes to get adsorbed, but yet the alkynes, which are still smaller in size and linear in size, they might get still adsorbed on the surface. May I clear it up? So therefore, these are called the barium sulfate, calcium carbonate, and nickel borate. These are called the poisons. And what they are doing is they are decreasing the activity of the metal surface. Hence this process is called poisoning the catalyst. So on poisoning the catalyst, you would notice that the triple bond will only end up getting up to double bond. Got it? Right. Now, if you may recall from isomerism that a carbon which has four different groups is projected as a chiral carbon center. So given a chiral carbon center, it is expected to be optically active if there is only one chiral center. Optically active means what? It means if you take that species and its mirror image, these two will be non-superimposable mirror images, otherwise also known as enantiomeric pairs. Any active mirror images which are non-superimposable are called as enantiomeric pairs. This basic definition is clear, Beta?
Yes,
Right.
sir.
Now, notice this molecule here. In this case, if my reference atom with respect to whom I'm discussing this idea is carbon, let's say, or sorry, is C in this case. If this C species is on the same side on a Fisher projection, this is called a Fisher projection, a two-dimensional form of showing how the molecule looks like. Okay. On a Fisher projection, if at all I keep both these groups to be on the same side, correct, then it is called erythrokind. Okay. And if I take the mirror image of the same, one second. If I take the mirror image of the same, you would notice that these two are non-superimposable. If you have non-superimposable form, again these two are enantiomeric pairs of each other. Now, if the same reference atoms in this case or reference species in this case are C and C, and here also C and C, in the Fisher projection, if they are opposite to each other, then you call it as a threokind. This was an erythrokind. Now we are talking about a threokind. Even if you take the mirror images of the threokind, it will be optically active and both will be enantiomers of each other. Got it? Now, what you would see that D2 is being added to a double bond here in the presence of nickel. So I will get a single bond. So I can express that in the Fisher projection. And in the Fisher projection, both the D's could be on the same side or they could be on the opposite side also like this. But here I'm talking about, suppose if they are on the same side, then you check out the mirror images of both of them. This is erythro, this is erythro. Those two are mirror images of each other. But what you will notice here is there is a plane that is passing through them, which will act like a plane of symmetry, isn't it? Because plane of symmetry means the above shape of the molecule and below shape of the molecule should look exactly same or mirror images of each other. So you can see there is a plane of symmetry passing through this. Since there is a plane of symmetry passing, these two are referred as mesoforms. And all mesoforms, all mirror images of mesoforms are identical. That means 1 and 2 are identical species. They are not different. They are not stereoisomers. They are one and the same. They are identical molecules. Clear, beta? But whether you will get erythro or whether you will get threo is to be learned from this basic trick you would always remember. That is, if you have a cis molecule and you make a syn addition, you are entitled to always get erythro as a product. Correct? If you have cis molecules and you have anti-addition done, you'll always get threo as the major product. If you make a trans molecule and then make a syn addition, again you'll get threo, trans and anti, you'll get erythro. Got it? Clear, beta? So you can always remember it this way. CSC, maybe computer science engineering. You can remember this way. Correct? Next, CAT, CAT, that is cis, anti, and threo form. TST, remember it like a test. Okay? EAT or TAE, eat. Correct? So these are the important clubbing of groups we should know. That is, if you have a cis form, syn addition, erythro. Cis form, anti-addition 3O, transform, syn addition 3O. Clear beta? See this example. If I take a trans molecule, add deuterium to it in the presence of platinum and heat, this is trans, and you know that metal addition, sorry, hydrogen or deuterium addition in the presence of metal is syn addition. So, needless to say, you should understand that it is syn addition, and which is giving a product which has to be 3O, because you can see on the Fisher projection these two are opposite to each other. So possibility is 50% of this you will get, 50% of this you will get. Now, if you are getting, if you are getting enantiomeric mixtures, like you can see this is an enantiomeric mixture, because this is a mirror images of this, and both of them does not have any plane of symmetry, hence they are optically active. Individually they are optically active, but if I take an optically active mixture of 50% and optically active mixture of another 50% and add both of them, then now if you observe its optical activity, it will be showing zero angle on the polarimeter, which means it is optically inactive solution now. Such a kind of solution is called racemic mixture. May I clear beta? So what you would notice is when you make trans to undergo syn addition, you will get 3O, but the 3O what you are getting is always racemic mixture and optically inactive solution. The logic applies the same in the case of cis also. If you have a symmetrical cis, that means both sides the groups are same, and then you add deuterium in the presence of platinum, and you know that this is a syn addition. So we expect this to be C, S and E. E means erythro. So both should be put on the same side. But what you would notice is there is a plane of symmetry in both of them, which suggests that these two are one and the same. Thus, they are optically inactive and they are mesoforms. Okay. May I clear it up?
Yes, sir.
Next. Next one is hydrohalogenation. That is, if you have a pi bond added with HX, okay, HX could be any mineral acids like HCl, HB or RHI, and you're expected to take it in a concentrated form so that it can undergo an addition. A hydrogen will get added here, X minus will get added here. So thus you will get this product. Now, suppose if you have a pi bond on an alkene, which means the pi bond is always going to be an electron rich species, thus it is a nucleophilic in nature. Okay, beta? And this nucleophile, when it attacks H plus, because H plus is sufficiently available because it is a mineral acid, and all mineral acids in this case are strong, so you'll have sufficient H plus available. So this pi would go attack on H plus, which will act like an electrophile to lead into a positive charge here, because now H plus when it is getting added, this pi could shift here and get added, thus giving a positive charge here, or this pi could shift here and then added, thus giving a positive charge here. So you might get two types of positive charges here. And the other day during intermediates, I told you, if I compare 1 degree carbocation and 2 degree carbocation, 2 degrees may, more stable. So you can see this is more stable carbocation. So stability will be 1 greater than 2. So definitely we expect this to form more. And once you get a carbocation form, then X minus will attack rapidly, because you can see there is a positive and negative sign attraction. So that makes you a major product of alkyl halide. Got it? Now, in this one important deal, what we need to understand here is that, you know, the first step where a neutral species is converting into a charged species, it might take time, because a stable molecule is going towards an unstable molecule. So definitely it will take some time, isn't it? Therefore, this is a slow process, and a slow process in a multi-step reactions is called as a rate determining step. So this is a rate determining step where a carbocation is forming. Got it? Now, obviously, the rate will be much progressive in the direction where it is more stable carbocation. If it is less stable carbocation, that speed will be even much slower than the stable carbocation case. So, if I write in terms of reaction, how it is happening. Suppose if there is a reactant here, alkene. From here, first it is going to a more stable carbocation here, and from there it is finally reaching to the product here. So this is the reactant, which is alkene, correct, plus HX. Now this is the product X, and what you get in the center is a carbocation. Clear, beta? Wherever there is a carbocation formation, there will be multiple transition steps. So this is the energy, highest energy, and highest energy form is called as the transition state. And you can see there are two transition states which are observed. Clear, beta? Therefore, if you notice the basic examples also, you will have a similarity here that when you have a double bond adding with concentrated HBr, first pi bond will go, take H plus, positive charge will start coming here first. But once you get a positive charge, it is likely to get shifted here because it can get more stable carbocation. So from here, hydrogen will shift onto this side, pushing the carbocation to reach here. Got it? This is called 1,2 hydride shift. Thereafter, Br minus can attack, and thus you are getting a major product as this one. Similarly, if you have a pi bond on a cyclopropyl pentyl group, this pi will go attack on H plus, you generate a carbocation. And once you have a carbocation just above the 3-membered, 4-membered, or 5-membered ring, they will undergo ring expansion. So bond will break from here. This will attack from here, pushing it to ring expansion. And even after expansion, this is still at secondary position, and that can be pushed towards tertiary position by getting a positive charge. Okay. So therefore, further rearrangement will take place, which is 1,2 hydride shift again. And once you get that carbocation, Cl minus will attack, and thus you will get the major product as this one. Am I clear on that?
Yes, sir.
Any issue here?
No.
All good? Right. Now, notice this is an unsymmetrical alkene. And so far, whatever we are dealing was also unsymmetrical alkene. On an unsymmetrical alkene, if you make H plus 2 get added on it, then I was supposed to get either this carbocation or I was supposed to get this carbocation. And because we learned hyperconjugation and reaction intermediates, we were able to say that this is a more stable carbocation, so reaction will drive in that direction. But when this reaction mechanism was not, standardized, those days, they didn't know how to differentiate these two. So what they said, if a positive charge is coming on a carbon which already lags hydrogen, a positive charge is coming on carbon which already lags hydrogen, then we say it is following Markovnikov's rule. Got it? But if a positive charge is cropping on carbon which already has more number of hydrogens, then we say it is following anti-Markovnikov's rule. Clear, beta? So Markovnikov's rule is about adding adding hydrogen on the carbon, hydrogen rich carbon, and pushing positive charge on hydrogen deficient carbon. And you may have noticed in all these examples, whatever I have done, it is all following Markovnikov's rule. May I clear it up?
Yes, sir.
Next. You see, if I have HBr plus H2O2, if at all we have HBr and H2O2, this also follows anti-Markovnikov's rule, and there is no rearrangement occurring here. Got it? In this case, it is not following exactly Markovnikov's rule. Instead, it is following an anti-Markovnikov's rule. Why is that happening? Let me show you here. Whenever you take peroxide H2O2 and heat it a bit or use light, any of this one or heat, oxygen and oxygen is a very unstable bond, so it will break into radical. So what happens? This HO radical will immediately react with the concentrated HBr, convert itself into H2O plus Br dot, and Br dot is again a radical, and Br dot plus this alkene, whichever the alkene which you have taken here, this one, when you take this alkene here, now Br is expected to be selective radical. Selective radical. See, selective radicals are those, right? Selective radicals are those which will try to get added to give more stable radical. Now suppose if at all Br dot will go and add here, one radical can come here. Okay. So there is a chance that I would get one radical this way, dot here and Br here. This is one radical. The other radical which I can get here is Br coming here and dot coming here. Correct? Now we learned this between 1 degree radical and 2 degree radical. In this case, it is 2 degree radical which is more stable. 1 second. Right. Close it. So therefore, these two would be the radicals which you are expecting. But which one will be major product beta? Because it is highly selective, this one will be major product. And since this is major product now, this radical further reacts with one more HBr. One more HBr. On adding that, you will get Br here and H here plus Br dot. Now, if you notice, this delta H is actually greater than 0 because in the first case, energy is required. In the second case, actually, energy is slightly released. In the third case, also energy is slightly released. Got it? That's why this reaction is most likely to happen, because energy released is a good sign that there is a chance of reaction happening. Am I clear, beta?
Yes, sir.
So this only happens with HBr. If you do the same logic for HCl, this will not work. Okay. So if you do the same thing for HCl, this will not work here. Got it? Let me
Yes, sir.
just write
So,
this
but
out.
why does it only work for HBr and not
Right.
HCl?
That's what I'm trying to write it here, beta. 1 second. Right. See, suppose if I do the same thing for HCl plus H2O2 and HI and H2O2. Okay. These two does not give anti-Marco addition. This does not give anti-Marco addition. Okay. Suppose if you have a pi bond here and if I add HCl in the presence of peroxide, this will still give an Markovnikov addition product. This is following Markov addition. Why this happens here is, if you have noticed this X dot which is forming in the first case, then here, if you notice this one, sorry, second case, when you have HO dot, HO dot plus X dot, uh, HO dot plus HX, trying to convert into H2O plus X dot. Here, delta H is actually greater than 0, which means this reaction is less likely to take place. So it will mostly stay in which direction? Backward direction. For which cases? for X being chlorine and bromine. Sorry, X being chlorine, only chlorine. Okay, chlorine and fluorine. Fluorine. Okay, fluorine is anyway not going to happen. Okay, but in this case, the second case, if you notice, where we have this dot forming here, let's say in this case, I have a double bond plus X dot, which is giving an X here and a dot here, like this addition is happening. In this case, now you'll notice that Hx is being, greater than 0 for X being iodine. So in the case of iodine, this second step is not likely to happen. Am I clear, beta? So which means in case of chlorine, this step is negating. In case of iodine, this step is negating. So peroxide has no effect on their way of getting added. Clear, beta?
So it only
That's
affects
why this,
bromine.
huh?
So it only affects bromine then,
Only
peroxide.
affects bromine. Yeah.
Okay.
Check out on alkynes. If you have an alkyne react with HX, right? You will make a similar addition. The pi bond will go attack on H plus. You will get a positive charge. X minus will get added up here. You will get this form. And when you add second mole of HX, again it will follow Markovnikov's rule. Reason being, if you get a positive charge here, the halogen which is present here can give back bonding and support and make it into octet completion temporarily till the next X minus attacks. Clear, beta? Therefore, you'll most likely see both the halogens attaching on the same side, and in both the cases, it is following Markovnikov's addition only. Okay, from alkynes to alkene or alkene to alkane, it follows Markov addition only. Done. Let's see the next one. Halogenation. Halogenation is also an electrophilic addition because you are again adding an electrophile here, where I'm adding X2 in the presence of CCl4 or X2 in the presence of CHCl3. Basically, I need a non-polar solvent or very, very less polar solvent so that the alkene get dissolved. Otherwise, alkenes are highly non-polar. They will not get dissolved easily. Okay. To make them a dissolved form, you always take a non-polar solvent. So now imagine if at all I take an alkene, add with X2, then I'll get a dihalides here. Okay, I'll get this dihalides. Okay. Now usually what happens here is chlorine-chlorine bond is like this. This is a sigma bond, this is a sigma bond overlapping, correct? So on this side of the part, there is a sigma star orbital. This side of the part, there is a sigma star orbital, which is empty. So the pi bond, which is a nucleophile, is in search with an empty orbital, which it will find on X. So therefore, the pi bond will go and attack on this empty orbital. Got it? So this X would get added up. One second. So you would notice that the pi bond would go and attack here on the empty orbitals here, correct? And as soon as this attack happens, the sigma bond becomes weaker and that will break. Got it? Now, what is the interesting fact here is, as soon as this pi bond attacks on X here, this X still have lone pairs on it, correct? So what will it do? It will push this lone pair onto the carbon which is slightly getting positive charge, because if carbon is coming from here, most likely this carbon will become positive charge. So lone pair will attack from this end. So therefore, what do we have here? We will have something called a halonium bridge. Am I clear with that? And X minus is been lost here. So have you noticed this halonium bridge is a syn addition here? It is undergoing a syn addition. And obviously, this was a neutral molecule and you're getting a charged species, so this will take time. Hence, it is a rate determining step as well. Once you get the halonium ion, now the next molecule or the X minus which is present in the solution already, it will act like a nucleophile and try to attack on either side. Well, in this case, it is symmetrical, so it could add on either of the side. So we'll get X minus here, the bond will break and both X will be present. The one thing to note here, okay, one thing to note here is this is a planar structure, right, beta? This is a planar structure. On this planar structure, if you're hitting from here or making a bond from here it is breaking. So eventually it is like one X got added here, one X got added here, isn't it? So how are they aligned? Anti, correct? Therefore, the final addition of both the X and X appears to be anti-addition only. So very important to remember, here it is always an anti-addition. Halogenation is always an anti-addition. What are the important points, beta? First, halonium bridge formation. Second, that is the RDS. Third, overall step is a anti-addition. Clear? Well, all of this is nothing but an electrophilic addition. The wording electrophilic addition or a nucleophilic addition is always based on the rate determining step. If at all I take an unsymmetrical alkene, react with Br2 in the presence of CCl4, one thing I notice that there is a halonium bridge first form. And then Br minus is likely to attack on more substituted side rather than less substituted side. Why is that happening? See it here. Suppose if you notice this halonium bridge here, we have Br with a positive charge here, correct? Now, obviously this positive charge will get distributed over these carbons because that positive charge get induced around the carbons, just connected to it. Now, because this positive charge is already present here, the methyl group will always support by plus I effect, correct? Isn't it? And try to stabilize that carbon. And because it is getting stabilized here, now what happens? This bond will start becoming weaker as compared to this bond. Here there is delta positive, and delta positive. But which one becomes weaker bond now? So if at all I take this as bond X and bond Y, bond length wise if you notice X is greater than Y, bond energy wise if you notice X is less than Y. Am I clear, bacha? So think about it. If a nucleophile has to attack, it will always try to attack on the case where the bond breaking is more easy. So which direction bond breaking is more easy? This direction. So this side nucleophile attack will be less. This side the nucleophile attack will be more, giving a major product on a substituted side. Is this logic making sense?
Yes, sir.
Right. So that's how you will get a bridged molecule converting into this, two bromine groups. Now these bromines are added adjacent to each other. When adjacent halogens are present, that is called vicinal dihalides. So what is the product you are gaining is vicinal dihalides here. And you can always apply the logic that if you have a cis form, you're making an anti-addition. What are we expecting? 3O. CAT, right? 3O. So you can notice that Br and Br are on the opposite side here. Br and Br are on the opposite side here as well. So chances are you will get 50-50% of both each, and both of them are mirror images of each other. So these are enantiomeric mixture of 50-50 percentage, which we call it as racemic mixture, and overall it is optically inactive. Clear, man? You can see adding a double bond here, adding a chlorine on a double bond here. This is also an anti-addition, and this is a cis molecule here because both the groups are on the same side. And if you take a cis molecule, what do I supposed to get? 3O form. So that's why chlorine one inside, one outside, that makes it 50%. And this will also become 50%. Overall, what are we getting is racemic mixture here also. Done. Next type of addition is hydrohalin addition. Hydrohalin means one halogen is added, the other one is OH minus is added. Usually, if you take halogen, in this case, you're only talking about chlorine and bromine because iodine is insoluble in water. So if I take chlorine and bromine and add it to water, you will see a redox reaction happening. Chlorine itself will get oxidized and chlorine will also get reduced. So a disproportionation reaction will be observed, wherein one halogen will get reduced as X minus, one halogen will get oxidized as X plus. So what you will get here is HOX and hypo oxo acid. This is an oxo acid and this is a mineral acid. You will get some quantity of mineral acid and you will get some quantity of hypo oxo acid. Okay. Oxo acid means an acid which is connected via oxygen. So you will get this as HOX. And obviously, if you compare electronegativity, oxygen is more electronegative than the halogen, chlorine and bromine. Therefore, this will always carry negative charge, this will carry positive charge. So there is a delta positive charge on the halogen, which is sufficient enough for the pi bond to go and attack. So the pi bond from here will go and attack halogen here, right? As soon as it attacks here, this OH minus will go away. And likewise, just now we learned that since it already has a lone pair, the other lone pair will back attack here to make a bridged form. So again, you will get a halonium form. And this time Cl X minus is not a nucleophile. This time OH minus is a nucleophile. Got this point? So OH minus will attack here, breaking this bond, and this is a major product you will get. Okay? Now notice, there was a JE question which was asked earlier, correct? Wherein the same question was asked and asked which are the possible products. Which of these are the possible products? Option A, it was given as, X and OH. Option B, it is given as X and X. Option C, it is given as, you know, sorry, X and OH. And option D, it is given as OH and OH. Got it? So out of this following, if you want to check which are the possible products here, okay? Sorry, not OH, H and OH here, okay? H and OH here, okay? Now, out of these four, tell me which are the possible products or which are not the possible products. First one we just learned, it is a possible product. Yes, in fact, that is a major product also. So this is major. Make sense? Second one is also possible product. Why? You could notice that there is some amount of X minus present, na beta? है कि नहीं? है, there is some amount of X minus present. Similarly, C. Is C possible here? No. Where is the electrophile going? Electrophile should always come on the end. Nucleophile should always come at the center. So the chances of forming this is minute, very less. So chances are very less. So we can say no. Okay. What about D? Again, here also, there is very tricky one. See, X plus is present in the solution and H plus is also present, na beta? H plus bhi to hai. HX is H plus only. So if there is H plus, there is a chance that pi bond could go and attack H plus. And once you get H plus, this OH minus as a nucleophile can attach. So the chances are, yes, there is a chance that this molecule can be observed. Clear, beta?
Yes.
What is definitely not observed, because there was the option like this also, where we had two OH groups. So they made it more easier with this question. So this is definitely not going to be observed. Got it?
Yes.
Right. Next, notice this one. I have a trans molecule here. I have a trans molecule here. and I'm adding a Br2. I'm adding a Br2 here in the presence of water. So bromine, when you add it to water, it appears a brown color solution. And in that brown color solution, you will have two parts, HOBr and HBr, because it will undergo disproportionation. After this disproportionation only, you will have these two colors, two molecules. And then you would notice that Br and Br can form here. Br and one OH will form. Correct? Sorry, I have to write OH. I have written OH here and here. Yeah. OH and OH. Okay. So since it is in bromine water, nucleophile will be OH minus, which is more stronger nucleophile than Br minus. That will attack here. Why? Because this is more, C2H5 will give more plus effect than CH3. So attack will be happening on this end. And this is trans and this is an anti-addition. Acha, trans and anti-addition, what should we get the product? Erythro. So that's why both should be written on the same side. So OH and Br, you will get both 50-50 percentage. Now the solution is entirely colorless. Now this entire solution is colorless. So you will get a racemic mixture with the colorless solution. Okay. So what have we done here is we used bromine water to detect the unsaturation on a double bond. Correct? We use bromine water to detect the unsaturation on the double bond. Clear, beta?
Yes.
Right. So bromine water is always used for detection of unsaturation. Now, similar to that, what are the other reactions which can take place? See, if I take ICl, NOCl, IBr, BrCl, you just need to figure out which will act like a positive charge and which will act like a negative charge. That means which is electrophile, which is nucleophile. You can see this is nucleophile, this is electrophile based on electronegativity. The next one I have already written. This is electrophile, this is nucleophile. Here, this is nucleophile, this is electrophile. So can you see accordingly the products? Yeah, right.
Yes.
Next, another electrophilic addition which you will notice is via hydration. That is via hydration. That is, if you have a double bond, you add H plus and then there is only water. There is no bromine or chlorine or anything. So then water itself will act like a nucleophile, thereby producing alcohols. Rest of the mechanism type is same. That is, if you take a pi bond, add with H plus, first you will follow Markovnikov addition and you will get this, and that is the rate determining step as well. Clear, beta?
Yes.
And once you get a carbocation, water will get attached. So you'll get this as OH2 plus, H minus is removed, and you'll get this as an alcohol. Right? Next again, the pi bond will go attack on D plus, water will attack, so OD will come, D will come. So overall, water or deuterium, heavy water is getting added. This is called simple hydration. It is following Markovnikov's rule. There is a chances of rearrangement. There will be always formation of carbocation. These are the important pointers you need to learn from hydration. May I clear, beta?
Yes, sir.
Another form of hydration which you will notice is oxymercuration demercuration. This is also typically used for hydration. Here, there are two reactions happening. The first reaction is called mercuration. The second reaction is called demercuration. This is the reagent used for mercuration, that is mercuric acetate in water. Second is demercuration, which is sodium boron hydrate used as a demercuration. The initial steps are easy here. The first step, what would happen here is this one. HgOAc in aqueous solution will always, ionize to a small extent as OAc plus ACO minus. So you can notice this will act like an electrophile. Okay. So pi bond will act on it. Pi bond will go and attack on it. Correct. As soon as the pi bond will go and attack on it like this. If you have a pi bond here, right? In this case, this is the pi bond I took. So this plus HgOAc with plus charge attacks here. So you will get a bridged form of mercury here, Hg plus OAc. This is the form which you will get, which eventually lead to the elimination of this group. OAc will leave here. So we will get this as Hg2 plus ACO minus. Now this is what we call it as mercurium bridge. So they just like halogen bridge, now it is a mercurium bridge formation. Got it? Once you get a mercurium bridge, now water as a nucleophile will attack on the more substituted. This I explained you why more substituted.
Yes, sir.
So water will come here, then from water H plus will leave, and now this mercury will have sufficient electronegative nature compared to carbon that it can break the bond and convert itself into mercury precipitate. Then what's happening to this carbon? This carbon is getting positive charge. So how would I negate that? By pushing an H minus. How will I get H minus? By getting BH4 minus. So BH4 minus is a reducing agent which is helping in demercuration. That means removing out mercury. Okay.
Okay.
Now, if you notice in the overall addition, hydrogen is added on the end, OH is added on the substituted side, which means it is still following Markovnikov's rule. Therefore, I could say that there is a Markovnikov's rule followed here. There is no carbocation and there is no rearrangement observed here. Am I clear, bacha?
Yes, sir.
Next, check out hydroboration oxidation. This is another reaction type. In this case, there are two steps happening. First one is called boration. Okay, this is called boration or hydroboration. Second one is called oxidation. The second one is undergoing oxidation. Okay. B2H6 diborane is a gas, and when you mix that gas with a liquid tetrahydrofuran, it will make a reaction. I mean, it will react with this tetrahydrofuran to form a complex and remove one BH3 molecule. And this BH3 will act like an electrophile. Of course, it has an empty orbital, so therefore it will act like an electrophile. And once you get an electrophile here, the pi bond would go and attack on the empty orbital here. Got it? And the H minus present on boron, that will push towards this carbon to get H minus here. And this happens simultaneously this way. From here, the bond is breaking. From here, hydrogen is making a bond. Boron is breaking a bond here. And there is one bond which is made here, this way. This is called a four-membered cyclic transition state. MCTS means membered cyclic transition state. Am I clear on that?
Yes.
So you will get this transition state. This is the transition state which you will get. Through that transition state, you will get this molecule. Now what you will notice is boron is again getting an empty orbital. So the second mole will attack again. How many times it will happen? As many times all these hydrogens are removed. So 3 times this would happen. First time I have shown you. 2 more times it will attack till all the hydrogens has been lost. So what is left now? Will be only left with propyl, tripropyl boron, isn't it? And if it is any other alkyl, you call it as trialkyl boron. Or in short, it is like R3B. Okay, trialkyl boron. Now, once you get a trialkyl boron, now you react that with peroxide in the presence of OH minus. See, what does OH minus do? Check out here. Okay. HOOH. This is the peroxide, right? And peroxide is an acid. If I react in basic medium, it will become HOO minus plus H2O. Now this is a nucleophile where R3B will attack. It has an empty orbital and HOOO minus will attack here. On attacking that, we will get this as boron having 3 R groups here like this with O, O and H. Again, OO bond is weaker bond beta. So this bond will break And to support that, immediately this R minus will go and attack. So what is left here now will be boron with R, O minus plus ROH. Correct? Now let happen for 3 times. 3 moles of H2O2, if at all you take it. 3 times this will happen. And what do we end up with? We'll end up with 3 moles of alcohols. And the other part, what is left is borate ion. Got it? Now, if you have noticed in the overall reaction, what happened here? If there was a double bond here, eventually hydrogen got added here and OH got added here, which means it is following anti-Markovnikov's rule. So HBO reaction is an anti-Markovnikov addition. There is no carbocation. There is no rearrangement that has taken place. Correct? I hope this part is clear, beta.
Yes, sir.
Now, if you notice the hydration, there are 3 reactions which we just learned. And this is the synopsis of that. Simple hydration, there is Markovnikov addition followed. Carbocation is observed. Rearrangement is possible. Oxymercuration, demercuration. Markovnikov is observed. Correct? It has no anti-addition, anti-Markovnikov addition. There is no carbocation. There is no rearrangement. In HBO, there is no Markovnikov. There is anti-Markovnikov addition. There is no carbocation. There is no rearrangement. Another important point that is to be noted here, is that, okay, only HBO is syn stereospecific. Syn stereospecific means it will make a syn addition on the double bond. The H and OH, both of them added on the same side, from the same end. In other 2 cases, there is no specificity. Correct? Right? So I'll specify that also. While others are non-stereo, while others are non-stereo specific. Done? Now, quickly note these points. If at all I have D3 plus, first what do you do? In the simple hydration, D plus is added, positive charge will come, positive charge will migrate, rearrangement will happen, and then OD will happen. Oxymercuration, demercuration, D plus will get added here. Okay, sorry, H will get added here because this is H minus which is getting added. And OD will get added here, no rearrangement. So this is the product you will get. In B2H6, H minus will get added here. From here, OD will get added. So this is the product you will get. Done? Next. Hydration on alkynes. How does it happen on alkynes? If you have a triple bond, try to add here. Again by Markovnikov, H and OH. What do I get? I will get this as ketone. Correct? Why? It will undergo something called tautomerism. Isn't it? It will undergo tautomerism. That is, if you have an enol form, enols are unstable, they will always end up getting into a keto form. This is called tautomerism. Clear, beta? Same logic applies to the next one. If I take HgSO4 in the presence of dilute H2SO4, this reaction is called Kuchro's reaction. Okay. Now, what is this? If you have HgSO4 to be added here, okay, if just like oxymercuration, demercuration beta, here also mercury bridge will form first, then water will attack here, you will get this molecule. Got it? And this will undergo tautomerism to get this keto form here. Okay. This reaction's name is called Kuchro's reaction. Is this point clear, beta? Next. If at all I take B2H6 in THF and H2O2 is being given, I'll make an anti-Marconi of addition H and OH here, and you'll get this keto form here. Okay, one second. See, next is SiA2H, SiA2BH. SiA2 means secondary isoamyl group. This is called secondary isoamyl. That is boron with this group here, 5 carbons. Boron with this 5 carbon group here. Okay. That with an empty orbital here and hydrogen. This is called secondary isoamyl boron hydride. Am I clear? So if you have SiA2BH, okay, secondary isoamyl boron hydride here, then this will also help in making the same reaction here, just like hydroboration. Only factor here why we use this is that if you continue with B2H6 again, this will undergo reduction and this will become an alcohol again, CH2OH. While if I continue to do with SiA2BH, this will not happen. So if you want to stop it only at aldehydes and ketones, you need a bulkier substrate, bulkier boron. So the bulkier boron will regulate any addition further. Okay, that's why SiA2BH is used. Okay. Next addition reaction which you will notice is hydroxylation. The next type of addition is known as hydroxylation. If you have an alkene and you are making a reaction with cold alkaline dilute KMnO4. Now this is a purple color solution, purple pink color solution. Okay. On adding that, what happens is it will become a colorless solution of this molecule. And this will give a syn addition. So what did we get here? We are getting vicinal diols. And vicinal diols formation is what we call it as hydroxylation. Clear, beta? Now the alternative reagent to Bayer's reagent is this one, osmium tetroxide. If I take OSO4 in the presence of a mild acidic condition, that also leads to formation of syn addition. While if I take a peroxy acid, here, correct? So in that case, the addition would go and convert into an anti form. So now you'll notice an anti addition happening. Clear? Now notice how this happens. If you have a pi bond here, when you react with MnO4 minus, right? MnO4 minus would make an addition this way, that is by forming a cyclic structure. Okay, this is called manganate ester. Manganate ester. Once you get a manganate ester here, if you may have noticed the structure of manganese, it is supposed to be M double bond O, double bond O, double bond O, and O minus. This is the manganate structure. Now, how many bonds it has? Now it has 1, 2, 3, 4, 5 bonds only, right? Right. Here we have double bond. Sorry. After pushing it here, again you will get one double bond here. So 2 and 2, 4. Okay. 4, 5, 6. So total we have 6 bonds now. So that means it got a positive charge on it. Okay. And then from here between manganese and oxygen, bond will break. It will become O minus. Here also bond will break. This will become O minus. Correct. Thereby, now manganese will have, how much? +3 charge on it, isn't it? Correct. Now, because both of them has lost, now we'll have +3 charge on it, right? So that can be compensated by adding OH here, isn't it? So if you have manganese M double bond O, M double bond O here, correct? So what I could say here now, because this would become O minus and O minus here. Sorry, my mistake. It should be M manganese minus because the electrons are being added to this, right? So because this pi bond is going, so electrons are pushed, so pi bond is coming here. So it should be minus. So if it has to be minus here, now what I can say on adding, now if these two bonds are left, now what do we have here is that one plus charge will be lost here, one plus charge will be lost here, leaving behind, one plus charge on manganese. So that's what I have written, MnO2 plus. Got it? And on addition of water, you will get this as MnO2OH. And this MnO2OH eventually becomes MnO2 as a precipitate. This will eventually become MnO2 precipitate. This is the PPT I'm talking about. This is the precipitate which you will get. Okay. Black color precipitate. And the solution on the surface will be colorless. So can I say that both these oxygens were connected from the same side? So that's why this is a syn addition. This is a syn addition. Am I clear on that? The same logic applies to osmium also, and this is called osmate ester. It is called osmate ester. And in this osmate ester, the oxidation state of osmium is plus 8. Sorry, here. Originally, it was plus 8. And after the reaction, if you notice, it has now, basically, both sides, this will lose out. And at the both sides, we will get OH groups added. So overall, now there are only two extra electrons which came on osmium, makes it as plus 6 oxidation state and convert itself into an osmic acid. In this case, there is a precipitate forming. In this case, it is an acid forming because this is in a basic medium. This is in an acidic medium. Am I clear, bacha? Next, peroxy acid. If you have any peroxy acid, that is C double bond O, OOH, this is peroxy acid. If you notice a peroxy acid, the pi bond present on the alkenes will attack on the peroxide oxygen, which is non-localized. That means these electrons are not going anywhere. In a peroxy acid, this lone pair is always in resonance with the C double bond O, but this lone pair is localized only. This is localized, isn't it? And when this bond breaks here, this will become O minus, this oxygen will become O plus. That's why the pi bond is always attacking on this O plus oxygen, and this will go out as O minus, leading into this epoxide form. Okay. And once you get RCOO minus, this O minus will take H plus and leave with a neutral molecule known as epoxide. Epoxides are nothing but three-membered cyclic ethers. Am I clear, bacha?
Yes, sir.
And if you have noticed, the pi bond got added here and this oxygen getting added from the same direction. So overall, what is the type of addition here? It is a syn addition. So first step is an epoxidation. This is the first step. So the first step is called the epoxidation. That's what I have written here. Okay. Now once I get an epoxide here, the reaction could happen in both acidic and basic medium. Now notice, if you take OH minus, which is a basic medium, if it attacks here, this bond will open and you will get OH here and O minus here. Got it? So then on hydrolysis, it will take H plus, you will get OH and OH. So this overall OH and OH are opposite to each other. So overall, it is an anti-addition. In acidic medium also, you will notice that first lone pair will take H plus, and you know that water will always attack on more substituted side. It will attack, this bond will break, again it will attack from the back side. So this OH and this OH were opposite to each other, making again an anti-addition. So therefore, epoxidation, if you use peroxy acid and epoxidation, then the overall addition is anti. But if I use cold dilute KMnO4, it is always a syn addition. So you can see this product. I took a cis molecule. I make a syn addition. I should get erythro. So you can see OH and OH are on the same side. So overall, I'll get racemic mixture. Okay. But if at all I take an peroxy acid and then add D3O plus, this is cis molecule. I'll make an anti-addition. So I should get 3O. So which is what you will notice. So OD, 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 OD are opposite to each other. Am clear, beta?
Yes,
Right.
sir.
Now, nucleophilic addition is not usually taught as a part of reaction mechanism. So as of now, I'm skipping it. Got it? Hmm. Right. Now, let us come to understanding of next important part of the reactions, which is elimination reactions. Got it? One second. See, whenever you have an alkyl halide and you react with a base, ETO minus is acting like a base. Then what you would notice here is the base is extracting H plus and X minus is leaving from here. That leads to the formation of double bond. How is that? See, if you remove H plus, what is left on this carbon? C minus. If you remove X minus, what is left on this carbon? C plus. So C plus C minus together will make a double bond formation. And that's how you'll get this double bond form and ETOH plus X minus formed here. Okay. One important aspect you need to notice here is we are breaking two sigma bonds in this case. And what is the result? We are making one pi bond here. One pi bond there and one sigma bond here. But two sigma bonds are more stronger than one pi and one sigma. Therefore, in the overall reaction, energy is required. So I could say delta H is positive in the overall reaction. Make sense? Next, if you have two molecules and I'm getting three molecules as a product, which means overall the number of particles are increasing, which means the entropy of the system is increasing. So I can say delta S of the reaction is greater than 0. So enthalpy change is positive, entropy change is positive. And if you notice, the spontaneity or the feasibility of a reaction depends on the sign of delta G. And delta G is equal to delta H minus T delta S. If you have learned thermodynamics already, you would know this. Otherwise, remember it like a formula that for a spontaneous change, delta G should be always negative. Now we learned this is positive, this is positive. When will this become negative? When the temperature is higher, right? Therefore, these elimination reactions are typically feasible only at high temperature. In fact, any elimination for that matter is always more favorable at high temperature. And that's what you will notice. Eliminations are favored at high temperature. Leaving group, which is a part of a substrate which leaves with the electron pair. Leaving group, which is a part of electron, it's a part of a substrate. And that if it is leaving with an electron pair, right, that will create that dent of positive charge on carbon. And base is extracting proton from beta position. Now notice this positions. Where halogen is removed, that position is always, symbolized as alpha, and the adjacent carbons are termed as beta. Okay. And usually the mandatory thing is that beta should always have one hydrogen, at least one hydrogen to be removed, right? Otherwise, we cannot make a double bond. So therefore, base will always extract proton from beta position. Any doubt here? There are many types of elimination reactions. Out of that, the first kind we will notice is E1. E1 reaction. Elimination 1. The one here represents the molecularity in the slow step. See what is the overall reaction. If I take a 3-degree alkyl halide and I react in a polar solvent like water, and heat it sufficiently. And I told you heat is mandatory for elimination cases. So if you provide heat, then you might get some amount of product as this one and the other product as this one. The major product is always an alkene. Okay. The substituted product here is a minor product. Got it? What is the step that happens here? Check. The first step is if you take alkyl halide, the slow step is slowly the chlorine is removed from here and getting a positive charge on the carbon and Cl minus is relieved. Now this is only going to happen if there is a support of polar solvent. Okay. So polar protic solvents like water, alcohol, acids, okay, increases the rate of reaction. Okay. So better the polar solvent, more is the ability to form this carbocation. Once you get a carbocation, chances are it can undergo rearrangement also. And once you get a rearrangement done, then the base will go and attack on these positions here. Got it? Because this is an alpha position. Now wherever positive charges, that becomes alpha position after rearrangement. And the next carbon will become the beta carbon. From the beta carbon, you will take a hydrogen away. Base will go and attack there. H is removed. And then a double bond is formed. But what is the base here? Because the solvent, you're taking only a solvent. The solvent itself will act like a base. So if we take water, water itself will act like a base. So water will extract proton from here, pushing this bond to eventually making it as a double bond form. Okay. And if you have noticed water, alcohol, acids, these are all very, very weak bases, isn't it? They do not have any charge. So E1 is only favorable when you have a much weaker base. If you have a stronger base, it will go towards the direction of E2. That's why you need to only rely on the solvent. So solvent itself has to act like a base. Okay, beta? Right. See? So if you notice here, one thing is there must be a stable carbocation. So therefore, the rate of E1 will be based on the stability of carbocation. You see this alkyl halide will make more stable carbocation. Then 3 degree, then 2 degree, then 1 degree. Methyl, there will not be any elimination at all. Got it? So you could notice that these are the relative weaker bases here. Okay. And most stable carbocation will always give you major product. So you can see first this is a compound given. Methanol I take in the presence of heat. That means you should anticipate it is going towards elimination. Remove the chlorine, make a carbocation. From the carbocation, make a rearrangement. Once the rearrangement is done, you use the heat in the presence of water, right? Obviously, you can remove H plus from here, double bond will be formed. Either this position or this position, because there are two types of beta. This is also a beta, this is also a beta, this is also a beta. But these two betas are same. So you can get one double bond here, or you can get one double bond on this side. Correct? Now, if you have a positive charge here, you can get one double bond inside, or you can get one double bond outside. Got it? So
Yes,
the
sir.
double bond which you are getting here on the outward and double bond which you're getting inward. Now just count the number of substitutions which you have. See, with respect to this double bond, 1, 2, 3. How many substituents we have? Three alkyl substitutions. With respect to this double bond, you have 1 and 2. This entire thing is one substitute. So two substitutes. With respect to this also only one substitute. So the one which has the maximum substitutes, that is called as Shezhev product. So this is a Shezhev product. And the other ones which are with a minimum number of or less number of alkyl groups, those are called as Hoffman products. So these two are Hoffman products. Okay. And here The product formation is based on the stability of the alkene, whichever the alkene is more stable. So which is more stable here? This one. Since this is more stable alkene, this will form as major product. Make any issue here?
No, sir.
Right. See, in generally, if at all I have to plot the energy graph, how would it go? So from the reactant, first you are going to a carbocation formation. From the carbocation, it might undergo rearrangement. See, it will undergo some rearrangement. So from rearrangement, finally it is forming a product. This is somewhere it has formed the product. Okay. So that means here we have an alkyl halide like this. Okay. From this alkyl halide, you have got this first carbocation. Then you have got the second carbocation. And finally, you will get this alkene. Okay. Since this is a more stable alkene, you will vouch for this as a major product. Done? Just to give you a briefing, polar protic solvents are these, which will have polarized hydrogen. Polar aprotic solvents are these, which do not have any polarized hydrogen. They have polarity, but they do not have polarized hydrogens. So ethers, ketones, aldehydes, esters, substituted amides, substituted amines. These are all polar aprotic solvents. Got it? And E1 is most favorable in which kind? Polar protic solvent. Clear, beta? Now, usually you will write rate of the reaction always as, rate of the reaction for E1 is equal to some constant into substrate. In this case, substrate is what? Rx. And that is raised to power 1 because there is only one substrate you are taking. See the mechanism. Only one substrate you are taking. So this is how you write the rate law. This is also called the rate law, or kinetically speaking, the rate can always be written for slow step. So in the slow step, only one reactant is been involved. So therefore, we can say the order of the reaction is 1. Okay. And molecularity is the number of molecules involved in slow step. So number of molecules involved in slow step is 1. So that's why it is designated as E1. The 1 represents the molecularity here. Okay, beta? I hope this part is clear.
Yes.
Right. Okay. So this is about E1 reactions. Okay. Now, one second.